So now we're going to talk about how you find the length of a polar curve as it sweeps from theta equal A to theta equal B. So we'll start with, remember the parametric equations, x equal r cosine theta or f of theta cosine theta, and y equal r sine theta or f of theta sine theta as theta goes from A to B. Now, so the formula for finding the length of a parametrized curve is L equals the integral from A to B, the square root of the derivative of x with respect to theta squared plus the derivative of y with respect to theta squared d theta. Now this is equivalent to the following. This is equivalent to saying the square root of r squared plus the derivative of r with respect to theta quantity squared d theta. And so we can use this formula in order to find the length of a curve, which you were probably called before arc length, but we're finding the length of a curve. So let's just set up some integrals. I don't want to go through and solve these, but let's set up the integral to find the length of the cardioid 1 minus cosine theta. Now the derivative of this cardioid is just sine theta. So the derivative 1 minus cosine is sine theta. And this cardioid is traced once as theta sweeps from 0 to 2 pi. So to find the length, we need to use this formula here, and we need to insert r squared. So we're going to put in 1 minus cosine theta quantity squared, and then we're going to insert dr over d theta squared, so that's going to be sine squared, and we're going to evaluate that from 0 to 2 pi. Now I'll do a little bit of manipulating here. If you square that 1 minus cosine theta, you're going to get 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. Well, cosine squared theta plus sine squared theta is 1, so you're going to get 1 minus 2 cosine theta plus 1. So you're going to get 2 minus 2 cosine theta, and I'll just factor the 2 out and say that's 2 times 1 minus cosine theta. And actually I lied to you. I said we're just going to set it up. I actually did solve this one. So then 1 minus cosine theta is actually 2 sine squared theta over 2. And then if you multiply this by 2, you get 4 sine squared theta over 2. And that's actually, if you can actually take that out of the square root and get 2 sine of theta over 2. And then when you integrate that, you get minus 4 cosine theta over 2. And I'll let you evaluate it from here. So evaluate this at 2 pi, and then evaluate it at 0 and take the difference, and you should get that it's 8 units in length. Okay, let's do another one. How about this limacon here? It's also sweeps from 0 to 2 pi on the theta. So the derivative is minus 4 sine theta. And so if we apply the same formula, we're going to put r squared here, 4 cosine theta plus 2 quantity squared, and then plus negative 4 sine theta squared. And then if I square this, I get 16 cosine squared theta plus 16 cosine theta plus 4. And in here, I get 16 sine squared theta. Okay, so I have 16 cosine squared theta plus 16 sine squared theta plus 16 cosine theta plus 4. And then if I factor the 16 out of these two terms, I get cosine squared theta plus sine squared theta, which of course is 1. So I get 16 plus 16 cosine theta plus 4. And then, so that is actually 16 plus 4 is 20. So that actually sets it up. And I didn't feel like taking the time to search for any formulas for this, so I just used an integral tool for the evaluation. So I cheated on this, but again, the hardest part is kind of setting it up and getting it to a point where you can evaluate it. But the integral tool I got gave me this value for the integral, 26.7298. Now we can also find what's the surface area of revolution of a polar curve. And so if we have a curve r equal f of theta, and as long as it has a continuous first derivative as theta goes from A to B, and if the point traces the curve exactly once as we go from A to B, then the areas of the surfaces generated by revolving the curve about the x and y axis are given here. So if revolving about the x-axis, if we revolve around the x-axis, the surface area generated would be the integral from A to B 2 pi r sine theta times this same integral that we had a minute ago when we were doing the length. So it's that same integral in both of these it's not same integral, same radical in both of these integrals. Now, if you're going to revolve around the y-axis, the formula is 2 pi r cosine theta instead of sine theta. So let me go ahead and show you how this works. It says find the surface area generated by revolving the right-hand loop of the lemniscate r squared equal cosine 2 theta about the y-axis. Well, I'm going to let you investigate the loop and see that that right-hand loop is actually generated as you go from minus pi over 4 to pi over 4. Okay, so that's going to be our limits of integration. Now, the formula is r squared cosine 2 theta. Now, we can implicitly differentiate this. So if we implicitly differentiate this with respect to theta, we get 2r dr d theta, and then the derivative of cosine 2 theta is minus 2 sine 2 theta. And then if we divide both sides by 2, we get r dr d theta is minus sine 2 theta. So we'll just kind of hold on to that for a minute. Okay, now I'm going to do some interesting things here because I know it works. So just bear with me here. Okay, so now we want to integrate from minus pi over 4 2 pi r cosine theta, since we're revolving around the y-axis, and then times the square root of r squared plus dr over d theta quantity squared. Alright, now I'm going to take that r and I'm going to put it inside the radical. That's not supposed to be there. So I'm going to move the r inside the radical and it'll become r squared. So if I take the r and put it inside, I get r to the 4th plus r squared dr over d theta quantity squared. And let's see, did I just copy that again right here? No, I'm sorry. Here's what I did. Then I can write r squared dr d theta quantity squared. I can write that whole quantity as r dr d theta quantity squared. Now what that does, remember a while ago I never actually solved this for dr d theta. I solved it for r dr d theta. Well, now I have the value for r dr d theta. It's minus sine 2 theta. So that allows me to just substitute that in for this when I get ready to. Okay, now, so let's substitute for r squared. Now remember, we know r squared is cosine 2 theta. So r to the 4th would be that squared. So that's going to be cosine squared 2 theta. And remember, we know r dr over d theta is just minus sine 2 theta. So we substitute that in and we get minus sine 2 theta quantity squared. Okay, so now we have cosine squared 2 theta plus sine squared of 2 theta in the radical. And we still have the 2 pi cosine theta out here. Okay, now the good news, cosine squared of an angle plus sine squared of an angle is just 1. So that simplifies nicely. So I just get 2 pi cosine theta d theta. Okay, and now we know how to integrate that. That's just going to be 2 pi sine theta. And then we do it from minus pi over 4 to pi over 4. And so we can keep the 2 pi out here if we want to. And so we have sine of pi over 4 minus sine of minus pi over 4. Well, sine of pi over 4 is square root of 2. And then sine of minus pi over 4 is minus square root of 2. So we have minus square root of 2. So we actually have plus square root of 2 over 2. Actually, square root of 2 over 2, I mean. So we have square root of 2 over 2 minus square root of 2 over 2. So that's going to be square root of 2 over 2 plus square root of 2 over 2. So that's just going to be square root of 2. So we have 2 pi square root of 2 for our surface area. Okay? All right. Let's do one more here. Set up the integral for finding the surface area of revolving r equal 2 cosine theta about the x-axis. Well, the graph is a circle symmetric to the x-axis. So we only need the graph of the upper semicircle, okay, which is generated as theta sweeps from 0 to pi over 2. So now, we know if we're going to sweep around the x-axis, we know we're going to use this formula, 2 pi r sine theta. So we're actually going to use, I moved the 2 pi out here to keep it out of the way. Now, r is 2 cosine theta. So remember, I have to have r sine theta in here. Well, here's r, and here's sine theta. Okay, now remember what we have in here. In the radical, we have r squared, and then we have dr d theta squared. Well, dr d theta from this is just minus 2 sine theta. So I have minus 2 sine theta quantity squared. Well, this is going to be 4 cosine squared. This is going to be 4 cosine squared. So when we add those together, that's just going to be 4. Because factor the 4 out, cosine squared plus sine squared is 1. Okay, so let's see where I'm at. So I have 2 pi times the integral from 0 to pi over 2, 2 cosine theta, sine theta, and then again, this is just going to be square root of 4. Okay, so now, so I have 2 pi times this, and now when I take the square root of 4 out of this, that's going to be 2, so 2 times 2 is 4, so I'm going to get a 4 here. So I have 4 cosine theta, sine theta, d theta. Now, right here, just stay with me right here for a minute. This right here, you can break the 4 up into 2 times 2, right? Okay, so let's move one of the 2's out here, 2 pi times 2, so that's going to give me 4 pi, and then leave the other 2 in here with 2 sine theta cosine theta, and remember 2 sine theta cosine theta is just sine 2 theta. Okay, so now we have, we want to integrate sine 2 theta d theta, which is just going to be minus cosine 2 theta over 2. So we integrate that, and we got the 4 pi there. Now, the 2 goes into the minus 4, gives me minus 2 pi. So I have minus 2 pi cosine 2 theta from 0 to pi over 2. Now I'm going to leave the minus 2 pi out here, and let's evaluate from 0 to pi over 2. So if you put pi over 2 in there, you're going to get cosine pi, which is minus 1. And then if you do cosine 0, you're going to get minus 1. So we're going to have minus 1, which is minus 2, times minus 2 pi, which is 4 pi. Okay? Okay, now, I actually went to a lot of trouble to prove a point here. You may have known that if you look up a formula for a sphere, because that's what we generated here was a sphere. If you look up a formula for the surface area of a sphere, you'll find that it's 4 pi r squared. Well, we just, when we rotated this circle, it created a sphere with radius 1. So if we use the formula, we can easily see that the surface area of the sphere would simply be 4 pi times 1, which is 4 pi. So I wanted to do that so that you could see that maybe where this formula came from, surface area of a sphere, possibly came from a problem like this. And so they were able to generate the formula by using integration and polar coordinates. So that completes this section.